So here we are down in the depths of the physics building, and what we're going to look at is the relationship between stress and strain. Now, Robert Hooke was a contemporary of Isaac Newton, and he first looked at the relationship between stress and strain for springs, and in fact the name that governs the force on a string and its relation to the extension of a string still bears his name today, and we call it Hooke's law. However, the spring constant that he came up with only applies to a particular spring. You go and get a new spring and you've got to recalculate the spring constant for that particular spring. What we're going to do here is look at something a little bit different. We're going to look at a property of the material, in this case a rubber band. Now, the person who came up with that in 1807 was called Thomas Young, and he related the stress on a rubber band or stress on a material to the strain on a material, and found that for a particular range of stresses this ratio was actually a constant value, and the constant value for a particular material we now call Young's modulus. So what we're going to do here is apply weights to a rubber band, and I've taken a rubber band here and marked off positions on it, so we're going to measure the extension between these 2 points that have been marked in ink as we load it up with weights. And we're going to put that into a spreadsheet, and from that we're going to be able to do a plot of stress versus strain for this rubber band, and from that we'll be able to see if we can extract a value for Young's modulus for the rubber that this band is made up of. So to start with, what we've got is we've got the bare weight stack on the bottom, which is a 50-gram weight. And if I measure the distance between these 2 points with a 50-gram weight attached, we can see that it's about 8.6 centimeters. So we'll add that to the spreadsheet here. Next, we're going to add another 50-gram weight and repeat the exercise. So now our total weight is 100 grams, and the distance between these 2 points is now 9.1 centimeters. So we're going to repeat this multiple times and take multiple measurements, and so we'll just fast forward through that process so you don't have to watch everything. So here we are at the end of loading it up. We've taken several data points, and our maximum load is 350 grams of mass. So obviously we'll have to transfer that in, convert it into a weight in the spreadsheet. So now what we need to do is go and look at our data in the spreadsheet and analyze it there. Now, before we go to the spreadsheet, we need to do a few calculations, because we need to put these calculations into the spreadsheet. So what we measured was mass m in kilograms, or the SI unit for that is, and then we measured the length of the distance between the rubber bands, points on the rubber band, and we measured that in SI units of meter. But if we're going to investigate the relationship between stress and strain, we need to be able to convert these into stress and strain values. So how do we do that? Well, first of all, what we need to do is we need to look at the system that we've got. So here's our badly drawn elastic band, and then hanging off the bottom of this we have our weight, and that, of course, weight is mass times the gravitational field. Now, if we look at the definition for stress, we can see that stress is equal to the force perpendicular to the cross-section divided by the area. So this, of course, is tensile stress, which is a type of normal stress. There's no shear stress here, so it's the perpendicular internal force divided by the cross-sectional area. And what we're assuming here is that the mass of the actual elastic band itself, or rubber band, is negligible, and it's only the weight of the weight stack that we added at the bottom that matters. So we're not going to worry about the actual force varying through the rubber band. We're just going to assume that we've got the only force is this weight on the bottom. So the perpendicular force is simply the weight, so this is simply equal to the mass that we have attached times the gravitational field. Now, the gravitational field, we're going to just use the value that we can look up in a book or online, and that is 9.807 meters per second squared, and we're just going to take this as a constant value. Obviously it does vary slightly over the Earth, and I don't know exactly what it was in the lab, but we're just going to take that as a constant value and assume no error. So for this value here, we're going to assume that there's zero error. So that gives us our force, but we're doing an experiment, and an experiment is not enough to just know the value of the force. We have to know how well do we know the value of the force, and so we need to be concerned about what's the error on our force, and we'll mark this as capital delta times F. And so here, if we've taken G to be constant and a fixed value that we've looked up, then the only error will be due to our uncertainty on the mass, and then that's multiplied by this constant value here. And Lorne and Taylor assured me that the error on the mass that we used is of the order of 1 gram, and so this gives us our uncertainty on the mass is just 1 gram, and we multiply that by the gravitational field, so that's 9.807, and this gives us the uncertainty on the force, and of course this will be in newtons. So that's great. We know the uncertainty on the force that we're applying to the rubber band. So the next question is now, well, what's the cross-sectional area? Well, the rubber band in question had a roughly rectangular cross-section, something like this, and so we have an X and a Y length, and so what we need to do is we need to go and measure these. And so to do this, we have a pair of vernier calipers and the rubber band. So what we're going to do is carefully measure the width and thickness in 2 dimensions to get the cross-section. So if we measure it here, we get a distance of 1.34 millimeters. And in the other dimension, if we just rotate it very carefully, and we've got to be careful not to crush it because of course it's rubber, so it would deform if I apply too much pressure. And if we look at it here, I get about 1.48 millimeters. And so those two multiplied together will give us our cross-sectional area. Okay, so we measured these using the vernier calipers, as you just saw, and so we find out that one of these lengths is 1.34 millimeters now, and the other length is 1.48 millimeters. And we're going to assume that the error on this measurement is plus or minus 0.02 millimeters, and the error on this measurement is similarly, since we use the same vernier calipers, is plus or minus 0.02 millimeters. So the question is now, though, is our area here is equal to x times y. So what we want to know now is what is the uncertainty on the area itself. We know the uncertainty on each of these individual values. What's the uncertainty on the total area? Well, if you remember, we can calculate this using partial derivatives. We have that delta A squared, the uncertainty in the area squared, is equal to partial A by partial x, because that's one of the variables, multiplied by the uncertainty in x, and then that is all squared. So that's the contribution from the uncertainty in x. And then we have to add to that, since we've got the variable y, we have partial A by partial y times the uncertainty in our y measurement, and that's squared. So since A is equal to just x times y, if we differentiate A with respect to x, keeping y as a constant, which is what this partial derivative means, then simply partial A by partial x is just y, and so this bracket here just becomes y delta x squared, and then here what we have is partial a by partial y. Well, that's just the differential of a with respect to y, keeping x as a constant, and so that of course just gives us x, and then that's multiplied by delta y, and then that's squared. So this is going to give us our uncertainty on the area, and of course what we want is we want the uncertainty without we just want the uncertainty without the square, and so we just take the square root of this, and this gives us the uncertainty on the area. And if you put the numbers in, since we know the uncertainty in delta x, we know the uncertainty in our x measurement and our y measurement, we know the values for x and we know the values for y, what happens is you end up with a uncertainty of 0.08 times 10 to the minus 6 meters squared. And if we put in the values for x and y here, we find that our area here is equal to, and what we're going to have to do now is we're going to multiply it by 2. Our total area is actually equal to 2 times x times y. And the reason for that is that of course we had the rubber band was a loop and it was supported here at the top, and then we had our weight stack here on the bottom. And so what we have is we have two cross-sectional areas supporting the weight. We have one here and one here. So it's actually 2 times x times y because of the fact that we had two sides to the rubber band. And so if we put in our numbers here, then our actual uncertainty is going to be 3.97 times 10 to the minus 6 meters squared. So now we know the area of the rubber band and we know our uncertainty on the area of the rubber band. And so we've got our force and we've got our area, and that's all we need now to calculate our stress. So if we go back to this, we have that our stress, and I'll call this sigma now, is equal to F perpendicular divided by the cross-sectional area. So of course what we need is we need to know what is the uncertainty on our stress measurement. Well, again, it's just as we had with the area, it's partial sigma by partial F, because that's one of the variables, times our uncertainty in the force, squared, plus, and then we're going to have partial sigma by partial A, because that's our other measurement, times our uncertainty in A, squared, and that's equal to the uncertainty on the stress squared. So what will that give us? Well, we can now say that our uncertainty on the stress is going to be, well, if we take the stress and differentiate it with respect to the force, what we're going to have here is just 1 over the area, right? Because the area, remember, we keep constant, multiplied by delta F, and that's squared. And then we add to this, so now we differentiate F over A with respect to A, and of course what we're going to get is we're going to get minus 1, because that's A to the power minus 1, times F divided by, and now we decrease the power by 1, so it goes to minus 2, so that's F over A squared times delta A. And that's all squared, and that gives us the uncertainty squared. So if we look at this, what we can see is that the minus sign here doesn't matter because it's in a squared term, so we can just get rid of that. We'll just say plus because it's squared. So minus 1 times minus 1 is plus 1, so that doesn't matter. And we know all the quantities here. We know the area, we know the uncertainty on the force because we just calculated that up above, and we know the uncertainty on the area because we just calculated that up above. So we've got the total uncertainty now on the stress, and all that's needed is just to rearrange it and make it a little bit prettier. And so one way to do this is to divide through by the stress itself, and I'll put that in brackets squared. So we're going to divide through by sigma squared, and this is going to be equal to, and here if I have if I'm dividing through by sigma squared, then I'm going to have dividing through by F squared over A squared, but of course when it goes inside this square bracket I'm just dividing through by F over A inside this square bracket here, and so this becomes delta F over F squared, and then plus, and then here again, remember, inside the square brackets I'm dividing by F over A. So I'm going to cancel this F and I'm going to cancel one of the A's, and what I'm going to be left with is delta A over A squared, which is of course just our error propagation formula for division. And so if I simplify this out, then I get the uncertainty in sigma is just equal to sigma itself times the square root of the uncertainty in the force divided by the force squared plus the uncertainty in the area divided by the area squared. And so that's my uncertainty in the stress. So I now know how to calculate the stress and its uncertainty. So that's half of the problem solved. Now we need to look at the strain. Okay, so for strain, and we'll just call this E, what we have is we have the change in length divided by the original length. So remember, this is a tensile strain, right? So it's a normal strain, and it's the change in length divided by the original length. Now, we didn't measure the change in length. What we did was we measured the actual new length with the stress applied, with the weight on the bottom. And so we can rewrite this definition as L minus L0, where L here is the actual length or the distance between those 2 points on the rubber band, minus the original distance between these 2 points divided by the original distance. And we can simplify that down a little bit further by expanding out the brackets, and we get L over L0 minus 1. Now the reason for doing that is that we then put all of our variables in this one term here. So this is the new length and the original length. They all go in this one term here, and then this is a constant. So for error analysis and error propagation, this of course doesn't change at all. It's a fixed value. So the one thing we now need to do is we need to go and measure the original length when there's no weight attached. So this is the length of the band without any weight attached to it at all, so there's zero stress on it. Now that's difficult to achieve for a rubber band because you've got to do something to hold it out so it goes straight. So this is about as good as we can manage. And what we get here, as you can see on the scale, is the distance between these 2 points with the least amount of stress possible is about 8.4 centimeters, so 0.084 meters. So what we've now got is that the original length that we measured was 0.084 meters. And because we could take the rubber band off and measure it on the desk, as you saw, we're going to say that we have an uncertainty in this measurement of 1 millimeter, so 0.001 meters. Now, for the length here that we measured during the experiment, we're going to say that we measure this. This was a little bit harder to do because I had to get the ruler next to the 2 points, and of course the 2 points stretched, so they weren't exactly points anymore. They expanded as the rubber that they were on expanded. And so we're going to say here that the error on this measurement is a little bit harder to do, so we're going to say 0.002 meters, so 2 millimeter accuracy on the new length measurement, but for the original length measurement, we'll say that we're a little bit more accurate and we could do it to 1 millimeter. So now the question is, what's the uncertainty on the strain? Well, if we look here and we can say, well, we want to know what's the uncertainty on the strain, and the squared value of that is of course going to be partial E by partial L times delta L, and then this is all squared. And then we add to that partial E by partial L0 times the uncertainty in L0 squared. Now we can do that differential. It's quite simple. It's in fact exactly the same thing that we did with the stress, it's just the ratio of two values, because of course the one here in any differential will disappear because it's just a constant value. So what we're going to get is we're going to get that this is equal to, well, partial E by partial L is just 1 over L0 times the uncertainty in L, and that's squared. And then we add to that, remember we get this minus sign because it's 1 over L0, so it's L0 to the power minus 1, and that's going to become L0 to the power minus 2, and then multiply that by L, which we treat as constant in the partial derivative, times the uncertainty in L0, and of course that's squared. And so what we're going to do is, again, we're going to divide through by L, we're going to divide through by the extension, and so what we'll get here, well, actually, let's just simplify it without worrying about that. So what we're going to get here is we're just going to take the square root, and so we're going to get delta L is equal to, and here what we're going to have is delta L over L0 squared, and then plus, because of course this minus sign here, when we square it goes away, and then plus, and we're going to have delta L0 over L0 squared times L. And then that's all squared. And so that's our formula for the uncertainty on the strain. Now we could simplify this a little bit further, but I'll skip the algebra and we'll just stick this formula straight into the spreadsheet. So now we can calculate the stress and the strain, and more importantly, we know the uncertainty on them. So this is something similar to what you should be doing in your labs. You should be looking and worrying how accurately you've measured quantities. But now we've done this, let's plot the stress versus the strain and see how that relates for a rubber band. So here's the spreadsheet, and you can see that we've added in the masses here in this column, and we've added the lengths into this column. Now, first thing to note is I've added two additional data points. The first of those is just the zero mass, so the length that we measured on the bench, the original length, so we get a point at the origin. And then I also went back and added one additional data point with 400 grams of mass attached, so 0.4 kilograms, and I measured the length, and this required a slightly longer ruler than I had when I was videoing. So here we have the strain, and so I'm taking the length that's measured here, so of course this is the zero length case, and subtracting off the original length, and then I'm dividing it by the original length. And so you can see that this increases as the length increases. And then here we have the error on the strain, and so here you can see this is the formula that we derived using our partial derivatives that we've put into the spreadsheet here, and again you can see that the error increases as we go down. The stress, the formula for the stress is just the weight, the mass here, multiplied by gravity, so that gives us the weight, and we divide that by the cross-sectional area, and the cross-sectional area is held down here in this separate table. So this is the value that we measured, it's the multiplication of those 2 millimeter measurements, and then this is the uncertainty that we calculated using our partial derivatives, and then of course gravity we have here as a constant value. So that gives us all the data points, and so now all that remains to do is to plot strain versus stress. So this is going to be our x coordinate for strain and y coordinate for stress, and if we do that inside the spreadsheet with error bars, then we get a plot that looks like this. And so you can see stress the y-axis and strain on the x-axis. No units, of course, for strain, it's a dimensionless quantity, and newtons per square meter for stress. And so this is the relationship between them. Now, rather than try and fit this with a straight line, what I'm going to do is I'm exporting the data out to an analysis package that we actually use at CERN. This was the analysis package that analyzed the data that found the Higgs boson and all the other analyses that we do on ATLAS. And so we're going to use that to fit a straight line to this data to see if it is actually consistent with a straight line relationship between stress and strain for a rubber band. Okay, so here we have the data from the spreadsheet now exported and plotted in this root package. So you can get it from root.cern.ch, but it's quite complex, so I'm not sure I'd recommend this. And you can see that we've got the strain on the x-axis as we had before, so this is dimensionless, and here we have the stress in newtons per square meter, and you can see that there's some relationship between them. Now, this is the idealized stress-strain relationship that we'd expect for a rubber band. And what we're trying to measure here is something called Young's modulus. Well, in general terms, we're trying to see how the stress and the strain are related. But what we have is we have a definition of something called Young's modulus that relates the stress to the strain. And what it says, this is only in terms of tensile stress and strain. And so we have the Young's modulus is the tensile stress divided by the tensile strain where the ratio is constant. So the Young's modulus is essentially we measure the tensile stress, we divide it by the tensile strain, and it's only defined where this ratio is going to be constant. So if we look at the idealized plot that we'd expect to see for a rubber band, you can see that there's a slight deviation from straight here at low values of strain. Then we get this region here where there's a linear relationship between stress and strain. In other words, the ratio is going to be constant. And then at high values of strain, you see this deviation here. So what does that tell us for this rubber band here? Well, you can see that we do get this region here where it's roughly linear. So here, then we do seem to see a roughly linear relationship here, or it appears linear. And out here, you can see that we're getting this deviation. So that looks good. But oh dear, what happens here? Because if I draw the plot here, or I do an estimate, we can see that it's not flattening out, it's actually getting steeper, and this here is the origin. This is the 0, 0 point. So we've got a problem here. This doesn't look quite like the plot. So why do we get this deviation? Well, the way we did the experiment was not the best way, because remember, we're trying to measure the tensile stress that's caused by the tensile strain that's caused by a tensile stress. But if I take this metal peg here, so this is a cross-sectional view through the metal support peg that we hung the rubber band off. If I have no stress on the rubber band, so before I attached any weight to it, I got this nice circular rubber band. And then what happens is when I apply the weight to it, I'll have to shrink the scale a little bit here, the rubber band deforms and I get a shape that looks something like this, where here we have the weights stacked on the bottom. So some of this weight here doesn't go into producing a tensile stress where we're stretching the rubber band, right, such as that. Some of it goes into deforming the rubber band from being circular into being this elongated shape that we show here. So this is what's happening down here at these very low values of stress, is that the stress is increasing, but it's going into a bending deformation and a bending strain, and that's partly compressive and partly tensile, but it's tensile not in the same way, it's not in the tensile stress that we're measuring here with a tensile strain. So it's not stretching the rubber band, it's deforming it and bending it. And so that's why we get this deviation from what we'd expect in the idealized case that we show here. The other difference is that we're dealing it with rubber. Now, Young's modulus was actually originally designed for materials other than rubber, and in most materials, so for example steel, you actually get a straight line through the origin and then a small and then the deviation here at high values. And in the case of a straight line through the origin, of course, this ratio of tensile stress to tensile strain is very useful because you can measure it from 0 here, right? So you can measure the absolute tensile stress and the absolute tensile strain. However, we can still measure Young's modulus for a rubber band. It's just that now, instead of measuring the ratio of stress to strain, what we have to do here is we take our data that we've got here, and then we have to fit a straight line to it, and then it's the gradient of this straight line that will actually give us Young's modulus for rubber. And it's only going to be, of course, defined in this region here, where there is what appears to be a linear relationship. It's not defined out here. This is not Young's modulus out here because we've deviated from linear, and nor is it down here in this region here, where again we're deviating from linear behavior. So next step, we need to fit the data with a straight line, find out what the gradient is, and then this gradient will give us Young's modulus. Okay, so now we've got the plot and we've got the straight line fitted to it, and this is the reason we wanted to export it into this root package from CERN, is that we can do what's called a chi-squared fit, and unlike a least squares fit that the spreadsheet could do, this chi-squared fit takes account of the size of these error bars, and it gives us this number here. Now, for a fit that's consistent, we expect a number, this ratio, to be roughly 1. Now you can see here that we're actually better than 1, so what that means is that these data points agree better with a straight line than you would expect from the size of their uncertainties. So what this probably means is I've overestimated the uncertainties slightly. But regardless, you can see that there's a very, very clear straight line, and the data is very consistent, actually more consistent with a straight line than we'd expect, but only by a little bit. Now obviously this is only valid for a particular region. This point out here is not on the line, nor are these points down here, as we discussed before. These were due to the fact that we're sort of stretching out, unbending the rubber band. And then this one here is because we're exceeding the region where there's this constant of proportionality. So the line here is the region where Young's modulus is valid. And so Young's modulus is defined for tensile stresses only, and so we have Young's modulus is the tensile stress divided by the tensile strain. Now, we've got the formulas for these. We used them in the spreadsheet already. The tensile stress is just the force that's perpendicular to the cross-section divided by the area of the cross-section, and then we divide this by the tensile strain, which is the change in length, divided by the original length. And so, simplifying this down, what we have for the Young's modulus is that this is equal to F perpendicular times the original length divided by the area, cross-sectional area, times the change in length, delta L. And this is equal to Y, which is Young's modulus. Now, if we look at this, here you can also see what the units are. Here, the units of this are newtons per square meter. The units for strain here are, there's no units. And so Young's modulus is actually measured in newtons per square meter. Now, if we do a little bit of rearranging with this, in the region here where this ratio is constant, and we have a constant Young's modulus, then what we can do is we can rearrange this, and we can get that F perpendicular is equal to the cross-sectional area times Young's modulus, here, Y, divided by the original length, L0, multiplied by the change in length, delta L. Well, if I look at this, and now going right back to the start of this online lecture, remember we talked about Hooke's law. Well, here is my force, F. Here is a constant, K. And here is my extension, X. So what I've shown is that in this region here, where the stresses and strains give a linear relationship, and so this Young's modulus here is going to be constant, then in that region, this value here is constant, and so I've got that my force is proportional to the extension, which is just Hooke's law for a spring. But now we've got a more general form of it, and it applies to an elastic band. But the problem is that it doesn't apply perfectly. It only applies in this region here. Now, what you will find, as I already mentioned, is that for many materials, and that includes things like steel, then of course what you actually have is you don't have this funny little bump at the bottom, which was partly due to our experiment, but also partly due to the properties of rubber, and that you actually get performance something like this, where this of course is your stress, and this is your strain. And then providing you're within this region here, below this particular strain and stress, then you end up with Young's modulus being constant and the intercept here being 0, because this does rely on the intercept being 0, or you normalize it to this point here, so you start counting 0 from the end of this line here. But for most materials, the actual intercept is 0, or very, very close to 0. And so for those materials, this relationship here, although it's using Young's modulus, it gives us Hooke's law for springs. And what we'll see in the next online lecture is that, of course, springs are a little bit more complex. They're not just simple tensile stress. There's shear stresses involved in there as well. And so for those cases, we're going to need to also see how shear stress and shear strain are related. And those are related by something called the modulus of elasticity, which is a more general relationship between stress and strain than Young's modulus. And so we'll talk about that in the next online lecture.